we could be starting to prepare and study for the final because it's going to basically cover everything from exam one, everything from exam two, and the last two chapters that we're going to cover over the next 2 weeks. Um, so hopefully in terms of, oh, question? Yeah, yeah. So I was going to mention that too, and thank you for asking. So homework 7 is the last homework. That one is posted for you. So after today's class, we should be able to at least get started on that assignment. And then we should be able to finish it by well, after next class, we'll have said everything that we would need to be able to complete homework 7. And then yeah, homework 7, we're back on the regular homework schedule that we had for the first like main part of the class where it's assigned this Tuesday and then it'll be due next Tuesday. And I'll have my normal help session this Friday. So that if we have questions on homework 7, then we could be getting help on those things. And then also I'll have a homework help session the following Friday, which will be focused on the reactor design problem. And that's kind of the idea is that we're not going to be assigned a new homework in the very last week. I guess there's technically this is the 8th week. You're not going to be assigned anything in the 9th week because hopefully that's when we're finishing up the reactor design problem. And then the week after that, um, which I guess technically is the 10th week now that I just say it out loud. I won't assign anything new in the so the last week is the 5th and the 7th. On the 5th is our last day of class. I won't assign anything new on that day, and then we'll have our exam on the 7th. So hopefully that. Yeah, so the final exam is technically set for 2 hours. So but yeah, I won't yeah, it'll be the same kind of format. It will be basically the same length as the other, like our other exams were for an hour and 50 minutes. So for a 2 hour exam, like I'm probably not going to adjust. It'll be very similar to the length of the previous ones. Um, thank you for your questions. If there's any other questions about any of that kind of stuff, feel free to let me know. I'm just going to pull up my slides and then we can get started. Okay. Oh, question?
What was already on the exam, or will it cover also topics that were done?
Yeah, so it'll be cumulative. It'll cover everything that we've talked about, but there will be like some more emphasis on the newer things. Like, so I can't tell you exactly like how it'll be broken down in terms of like a percentage of exam one and exam two, and then these last two chapters. But yeah, there will be bits and pieces from the earlier stuff on there too.
Like I said, different topics added on.
Gotcha. It will be cumulative for all of the material that we've covered. So, like, if you look at your homeworks, for example, from homework 1, and you look at all of the different questions that you were asked, there were things that you did on the homework that you were not asked on the exam. You should not take that to mean that if you saw it on if you didn't see it on exam 1, that I couldn't ask you about it. I could ask you anything that we've covered in the course for the final exam. And so expect exam 1 stuff, expect exam 2 stuff, expect stuff from any of those homeworks, and then expect stuff from homework 7 and what we cover in the next 2 weeks. Question?
Are you?
Yeah, so I was gonna probably so if I go back to my schedule or just like the calendar basically, we're gonna have class today. We're gonna have class on Thursday. And then next Tuesday and Thursday is a normal week of class. And I will have covered everything that I want you guys to, that I would test you on by then. When we have normal class on Tuesday the 5th, that'll basically be like our exam review day. And then our exam will be on Thursday. So I will post the exam review before the 5th. I'll probably post the exam review like around on the 29th. The idea being that we would have about a week to be kind of preparing for ourselves. And then this exam review on the 5th, like we've covered all of Svekhov's notes, which is like 600 pages. So I'm not going to be able to do like any of that justice if I try to review all of it myself. So my hope for that review session would be that it would be kind of like the way that we set up the homework help sessions, where y'all come in, any questions that you have, we basically just use it as like an hour and a full class time of Q&A and getting help on if we need to like work on if there's homework questions that we have problems about or anything that we're wondering about, we could go through any lingering questions that we have so that we're getting any of those questions addressed before the exam. So hopefully that sounds good, and that was going to be the plan for that. And thank you for the question. Um, so today we're starting chapter 8, which is about the nuclide production and destruction. So today we're going to develop those equations, and then next class we're going to talk about solving them and doing some seeing what we can do with these equations. But a lot of this is hopefully we're going to see is basically just review and kind of applications of stuff that we've already talked about. So let's get into it. Um, Last unit, we were talking about reactivity changes and all of the various things that could be affecting the state of our reactor. Um, In this unit, we're mostly focusing on the first two, which is fuel burnup and then fission production, fission product buildup and decay. So basically, what we kind of want to think about is like if we were building a reactor and we were running it for the first time, we're going to be putting fresh fuel in that reactor. If it's like a traditional light water reactor, then those are going to be like those UO2 kind of like ceramic fuel pellets. So the fuel initially is uranium-235 of some enrichment, it's uranium-238, and then it's oxygen. And once we turn that reactor on and we start fissioning that fuel, we start depleting the isotopes. The amount of uranium-235 will slowly decrease in our fuel because we're burning it up. And as that uranium fissions, we produce all of these new isotopes. We produce all of these fission products. So you both have, if our fissile fuel is being burned up, that means that our fuel is kind of like losing its reactivity over time. Also, as our fuel fissions, we're building up all of these fission products. Some of those fission products are highly absorbing, which will further impact and like reduce effectively the reactivity of our system. So because of the fission, the fuel fissioning and what that brings into our system, we have reactivity effects because of burnup and fission product buildup and decay. And those are the things that we're going to be talking about and focusing on today. Um, just like we have different things that can contribute to changing the reactor state, these things can happen over different time scales. And so when we talk about different like classes of problems in terms of short and intermediate and long problems, it's basically like over what time scales and are we considering our reactor and what physics is most important in those time scales. So when we're talking about like short time problems in seconds to minutes, those are mostly going to be situations that cause our reactor to quickly have a reactivity change, which would be maybe some kind of accident scenario, some kind of control rod removal or insertion, something that happens over a short amount of time. And those things can basically, if it's a short time problem, we can use those point reactor kinetics equations to reasonably approximate how that reactor would behave as time moves forward after that accident happened. When we start talking about intermediate problems, so like hours to days, we have fission products that are building up. The buildup of those fission products changes the reactivity of our system. And if we don't account for the buildup of those fission products, then our point reactor kinetics equations are not going to be accurate for anything past like hours or days. So you can still use the point kinetics for like intermediate time problems, but you have to more carefully account for the buildup of fission products, probably by making your K effective or your reactivity change as some function of time that incorporates the fact that as the products build up, your K effective is impacted by that product buildup. And then we talk about even longer depletion, longer time problems, or what we call depletion problems. Those are over days or months, and that is where the actual like detailed changes of the composition of the fuel becomes more important. Um, and so those are the intermediate and the long time problems are what we're going to be focusing on more. We kind of already dealt with the short time problems when we were doing the point reactor kinetic stuff. Um, so when you are designing a reactor, you are very concerned about how does that reactor behave as a function of time. And basically, if you are designing and trying to like license a reactor, you have to prove to the NRC that this reactor is basically going to be safe, or at least yeah, that if there is an accident, you have a way to respond to that accident under basically any plausible accident that your reactor could encounter. Today we're going to start focusing on some of those longer time scale problems. And to do that, we're going to need to know about the composition of the nuclides in our reactor and how those nuclides build up as a function of time. So if thinking about what we were just saying, like thinking about how we have fresh fuel, that fuel is burning up, that is changing aspects of our system, that the fission process is giving us changes in our core composition. And if the core composition changes, what are some features of our reactor or some like nuclear physics quantities that might be impacted by these core composition changes? Our cross sections are going to change perfect. So it's going to remember that our cross sections, and I'll just put sigma x because it really could be any kind of cross section. These things vary as a function of position and as a function of energy. And they could vary as a function of time, especially if we're talking about how um, in our fuel, if we're accounting for composition changes, then that means that the materials in our reactor are changing, which means that the like average macroscopic cross section of our reactor is changing too. So it's going to absolutely change our cross sections. If it changes our cross sections, what's the other thing that that would probably have an impact on? Sorry? Yeah, so it's going to affect the number density. And really, the number density is kind of part of really because if yeah so technically the number density is kind of like baked into the sky and whenever we what do we typically when we do calculations we're for like reaction rates we're typically taking a cross section and multiplying it by something else. What's the thing that we usually would multiply a cross section by to get like a yeah, the flux, right? And that's another big one that's going to change because as and so our scalar flux, right? That also can vary with position and with energy and with time. And the scalar flux in our reactor is going to change if our cross sections change. Like if somewhere in our reactor we start building up a bunch of neutron poisons that have very high absorption cross sections, then that's going to take away the neutrons near that absorber. So the flux would change as a result of those composition changes. If the flux changes and our cross sections change, what about what about the outputs of our reactor are going to change? K effective, right? So if we think about our K effective, if we're changing the materials in our reactor, then we're changing their cross sections, we're changing the flux. And if we're changing the flux, that means that we could be changing the production and the loss rates in our system, which would impact K effective because it's just basically how is the production and loss balanced or out of balance. And then the other thing in terms of outputs of our reactor is like, if we wanted to know how much power the reactor was producing, it would involve the fission cross section, it would involve the flux, it would involve like kind of integrating that over the whole reactor. So ultimately the power of our reactor is going to be impacted by this too. Power could also vary as a function of position and energy and time. And so I'm just going to put a comma and a dot 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 because we could probably just spend another really long time thinking about all the different things that are impacted by changes in composition, but those are like some of the most important ones. And so, as a result of that, the depletion of our fuel becomes something important that we have to calculate and that we have to factor in to our like reactor design and reactor analysis because ultimately when we turn a reactor on um, large reactors like the AP-1000 or other reactors that are producing power, do y'all know how long they operate before they have to like shut down and refuel? You don't have to know like an exact number, but maybe like an order of magnitude. Like, is it days? Is it months? Is it years? They cycle through. It's a more than it's they vary. They're usually on like 18 to 24-month cycles. So you put all this fuel into your reactor and then you don't unfuel the reactor for 18 to or 12 to 12 like 24 months or so. So very long time that fuel is in there. It's a very kind of important calculation to say how much fuel do I need, of what kind of enrichment, arranged in what sort of way is going to be able to have my reactor produce, like if it's an AP-1000 and it's producing 1,000 megawatts, how do I get the system set up so that I can produce 1,000 megawatts of power for a full 12 or 18 months without having to shut my reactor down? That involves very, very careful planning in terms of what does my fuel look like? How does my fuel change? How do I have other elements of my system set up so that I can account for these reactivity changes as a function of time? And so ultimately, to do this, we have to be tracking the composition of the materials in our core, and the quantity that we would use to keep it track of that was the thing that was mentioned earlier, which would be the density of our particles, right? If we want to know how is the composition changing, that's going to be described by the atom densities of all of the different things in our reactor. So ultimately, we're going to be concerned about the atom densities of every material in our core. And we use capital N for atom density. The atom density can change as a function of position and a function of time. And it's a atom density. So what should the units of an atom density be? Yeah, atoms per centimeter cubed or meters cubed, but yeah, atoms per unit of volume. So that's the quantity that we're going to keep track of. And if we could, ultimately, what we would want to do is be able to say for every single isotope in my reactor, what is its atom density? And how does that atom density change as a function of both time in my reactor as well as position in my reactor? And this could be for any of the materials in my reactor, in the fuel, in the coolant, in the structural materials, etc. Um, so if we know, suppose that we like designed a reactor and we knew exactly what the energy dependent neutron flux was everywhere in our reactor. Um, if we wanted to talk about why the atom densities of different things in our reactor might change, what would be some of the processes that would result in us maybe producing new nuclides in our reactor or losing nuclides in our reactor? What are like the processes that are going to influence like the production and the destruction of nuclides in our reactor? Perfect, right? So fission, and we could lump these all as being a gain or a loss. Um, so fission is one. Is fission a gain or is fission a loss? It's a gain if you're talking about what the fission produces. Like if we talk about fission products, fission is a gain. But if we talk about uranium in our fuel, then fission is a loss because every time we have a fission, it's because of uranium or some other high actinide fissions. So fission is both a production and a loss, depending on what nuclide we're keeping track of. What other things could reduce could produce or lose an atom or a nuclide in our reactor? Decay, right? A lot of these nuclides that we end up producing are radioactive, and also um, basically, yeah, a lot of the fission products that we produce are radioactive. Uranium itself is to an extent radioactive, although its half-life is so long that usually we could probably ignore that in our calculations. But and decay is also both a loss and a gain, depending on what nuclide you're talking about, because some nuclides will decay and therefore they will lose themselves because they are decaying and producing something else, but also a nuclide can be born because something decayed into that nuclide. So decay can both be a production and a loss. And then the other one is kind of like is basically just any kind of capture reaction. So that's the other thing that we could talk about is just capture reactions. That would be a kind of reaction where a neutron comes in, the nuclide absorbs that neutron and doesn't fission, but just becomes something else. It absorbs that neutron and then and captures it and then becomes something else. So the capture is also a loss mechanism and a gain mechanism depending on what nuclide you're talking about. Like uranium-238 will absorb a neutron and that will turn into a new element, a new isotope. So that removes uranium-238, and ultimately what it ends up doing is producing plutonium 239. So capture, all of these, the fission, the decay, and the capture, can both be a gain of nuclides or a loss of nuclides, just depending on what nuclide we are talking about. And fission and decay and capture could all be characterized by their own reaction rate densities. So a reaction rate density would have units of like reactions per unit volume and per unit time. So if we wanted to talk about like the fission rate density, and we want to talk about this as a function of position and time, if I know the energy dependent scalar flux, and I want to get the fission rate density, what would I do with the scalar flux, the energy dependent scalar flux? Multiply by the fission cross section. And so what are the units? Can y'all help me remember what the units of the energy dependent scalar flux are? Perfect. Yeah, and you could have also said path length per unit volume, so you could have had like neutron centimeters up top and volume on the bottom. But yeah, it's like centimeters squared per second per unit energy. So it is true that we're going to take our sigma f, and our sigma f also could be a function of position and energy and time, and we're going to multiply that by our energy dependent scalar flux, which could vary with position and energy and time. But when we multiply those two things together, the scalar flux is the energy dependent flux has these per EV units. So if we want a fission rate density that just has these units of reactions per unit volume per unit time, we need to do something with this expression. And what would we do with that expression to basically get rid of the energy units? Integrate, right? We would integrate over all neutron energies. So we just take this and we'd integrate from 0 to infinity dE. And that is going to give us our fission rate density. And we could rewrite this a little bit because, like we were talking about before, our cross sections, like anytime we write a cross section, like a macroscopic cross section, it's a microscopic cross section times a number density. The microscopic cross section is what contains the energy information. The number density is basically what contains like the space and time information. So if we were to rewrite sigma f as microscopic for fission times the number density in my reactor, the number density isn't going to change with energy. So therefore, if I make that substitution in here for sigma f, then the number density can be pulled out of the energy integral. So I could rewrite this as my number density as a function of position and time, and then an integral over all energies of just my microscopic fission cross section, which only varies with energy, times a phi of R E T and a D. So this is just hopefully helping. Oh, question?
That, lowercase sigma,
Yeah. Yeah, because basically what we're doing here is we're saying that this, let me do a different color. We're saying that this quantity, sigma f, we're saying that that's just equal to little sigma f times the number density. And so this is my number density that I've pulled out of the integral because it's not, doesn't depend on energy. And then the little sigma f stays in the energy integral because it is a function of energy. And so hopefully this is kind of, I'm showing this out mostly so we can review our definitions of like a reaction rate density and how you go from this product right here, sigma F times phi of E, that's like my energy dependent fission rate density. And then when I take that energy dependent fission rate density and I integrate it over all energies, that's what just gives me the regular fission rate density and knocks out the EV units. And this is showing us how this reaction rate density actually depends on both the number density of the materials in my reactor as well as the scalar flux of the materials in my reactor. And so, based on that definition of a fission rate density, if I wanted to write a capture rate density, which could also vary with position r and time t, what should the, if the fission rate density looked like that, what should the capture rate density look like? Perfect, right? The only information really that's different that's contained here is just what type of reaction is it. So is it fissions per unit distance traveled or is it captures per unit distance traveled? But ultimately, that's exactly right, that we're going to have effectively the same exact expression, but just with a sigma capture. And so sigma capture could vary with position and with energy and with time. And our flux could also vary with position and energy and time. And if we take that expression and we integrate it over all energies, what's inside here would be my energy dependent collision rate density. And if I integrate the energy dependent collision rate density over all energies, then I just get the, and sorry, capture rate density. C is for capture. Then I get the number of captures per unit volume per unit time that are happening in my reactor. And we could play a similar game with the number density here too. We could rewrite the sigma capture as a little sigma capture times a number density, pull the number density out, and then we would have something that looks like we had before, but just with a microscopic capture cross-section, microscopic capture cross-section, instead of a fission cross-section. And D. So that's the nice thing about these reaction rate densities is that if you can remember the formula for any generic reaction rate density, it's the same formula for any type of reaction. You just have to remember to change the cross-section. And then the decay rate density, which also could vary with position and time. The decay rate density is going to look a little bit different because decay is not a fission-induced reaction. It's a basically like a nuclear physics kind of related process. Um, and we've seen the general formula for radioactive decay. If I have some like number density and I want to know the decay, I just usually take that number density and then I multiply by the decay constant for that material. So that's all that the decay rate density would be. It would be some decay constant times the number density for my material. And so hopefully that one is also like we've seen that before when we were doing those decay chains, right? The only difference here is that our n is now representing a number density instead of just a number of atoms. But that means that this is just decay rate density. So it's the number of decays per unit volume and per unit time. This is the thing that has the per unit volume information. The decay constant has units of inverse time, and that's what picks up the the 1/time information. So all of these quantities are reaction rate densities that have units of numbers of reactions per unit volume per unit time. This would be the number of the fission rate density is the number of fissions per unit volume per unit time. That's the number of capture reactions per unit volume per unit time. That's the number of decay reactions per unit volume and per unit time. And those are going to be the processes that are governing the production and the destruction of nuclides. So in terms of new processes, there are none. We're just talking about things that we've already learned, and we're just kind of putting them in a new context. Um, so some of the specifics of those reactions are shown here, and hopefully this will help us illustrate how each of these reactions can be both a production and a loss. When you think about fission, for example, you start with some nuclide X and a neutron interacts with it. The neutron is absorbed into X, so we form a compound nucleus where the mass number of this new nucleus gains 1 because the neutron was absorbed. And then what that compound nucleus does in a fission reaction is it splits and you get two fission products. So you get like an X1 and an X2. You get some number of prompt neutrons. And all of this stuff that comes immediately out of the fission reaction has about 200 MeV of energy that's associated with it. So if we're talking about tracking this atom X, like uranium-235, fission is a loss. But if we're talking about tracking fission products that are born from fission, like xenon-135, then these then fission is a gain for these things that are coming out of the fission reaction. Similar thing with capture. Capture is another form of absorption. So it looks kind of like fission at the beginning, where some nuclide absorbs a neutron and we form a compound nucleus. But instead of the nucleus fissioning, the nucleus de-excites itself by just emitting out a different particle. So the nuclide might just emit a high energy gamma ray. And then that original nuclide that was X has now become X, but with one extra neutron. So it becomes like an isotope of that original nuclide X. And the other way that it can de-excite is by kicking out an alpha particle. And so then this element becomes this X becomes a new thing because it's now lost 2 protons and it's lost to yes, it's lost 2 protons and it's lost 2 neutrons, so it's lost a total of 4 from its element. So if you're talking about like uranium-238, then capture is a loss for uranium-238. But then if we're talking about producing something like plutonium-239, then capture is a gain for that. And then we've talked about decay too. We've seen these decay chains. You could have some element or some isotope X that decays into J, that decays into K. And then if we're talking about like element I, then decay is a loss because every time it decays, it's losing some of itself. Whereas for this element J, it gains because I decays into it, and it loses because it decays into something else. So for decay, you can have gains and you can have losses as well. So fission reactions are going to reduce the concentration of what kinds of nuclei in our reactor. Technically, it would be fissionable means that it can be fissioned by a neutron of any energy. In general, the thing that can be fissioned by neutrons of any energy would be a fissile. So in the most general way, we'll say fissile. And that would be like, for example, 235 uranium or 239 plutonium. Technically, it would reduce the concentration of fissionable nuclides too. So I guess we could say both. We could say fissile and we could say fissionable. And so what's an example of a fissionable nuclide? Yeah, 238U is fissionable because technically it could absorb a very high energy neutron and then fission. So technically fission reactions would reduce the concentration of anything that's fissile or the fissionable nuclides as well. When nuclides fission, they produce a wide variety of fission products. Fission products And it produces these fission products in varying concentrations. We'll come back to that in a minute. When you have these fission reactions, you produce these fission products. Those fission products, do they just stay in the reactor as fission products, or does something happen with those guys? Perfect, right? Those fission products, they are highly radioactive. They will eventually decay into other nuclides. So whatever we produce right out of fission doesn't just stay there. Those things also will decay and produce other things as well. Um, so that's what happens with the fissionable things or the fissile things. Capture reactions, those are going to reduce the concentrations of what we would call fertile nuclides. So technically, 238U is also fertile. And that means that uranium-238 can absorb a neutron. It can transmute into something else that is a fissile nuclide. So uranium-238 can capture a neutron and then become plutonium-239, which is fissile. Another common fertile nucleus would be thorium-232. And what thorium is very similar, thorium can absorb a neutron, and then it will go through a bunch of decays and eventually become uranium-233. And uranium-233 is also a fissile isotope of uranium. So capture reactions will reduce the concentration of these fertile nuclides, and it will build up the concentration of transmutation products like plutonium-239 or uranium-233 if it's a thorium chain. So those are some of the specifics of those gains and losses and helping us just remember our terminology and what kinds of things get produced from these reactions and what kinds of things get lost from these reactions. Um, we this is basically just a reminder of how like what our solving approach is for different classifications of problems. So if it's a short time problem, that's when we can kind of ignore depletion of the fuel, and we can basically just use the point reactor kinetics equations to say how does the reactor evolve with time. Um, I didn't mention this during exam 2, but it is worth knowing that you can use feedback and the point reactor kinetics equations together. And so even if you have a reactor with feedback, for short time problems, you can still use the point kinetics equations. You just have to modify the point kinetics equations so that they can account for feedback. And this is an example of how those equations kind of evolve if you include temperature feedback. So you have the same like two original point reactor kinetics equations, but then you have a power equation, and this power equation basically relates how energy going into, doesn't this look like MC sub P delta T? And that's all that the power in your reactor is. It's just the mass flow of the coolant in your reactor times the specific heat of the coolant in your reactor times the delta T of the coolant in your reactor from what its temperature is at the inlet to what the temperature is as it goes through. And once it gets to the very top, it will have gained some final temperature. And if you do m dot C sub P delta T, that'll give you a measure of the power of that reactor. So if you work that out for the AP1000, you should get a power that's around 1 megawatt. And so this gives us a way that we can relate how much power we're producing, power P, to a temperature of the moderator T. And the temperature of the moderator is related to the coefficient, the temperature reactivity coefficient for our reactor, which would basically be a fuel coefficient plus a moderator coefficient. And then we can relate the temperature of the fuel to the temperature of the moderator as well. This is basically doing like an energy balance on the fuel, because if you think about the fuel itself, the fuel has a temperature change. Its temperature is changing, and its temperature changes because of energy that it produces. the fuel heats up because it produces power. So it has a gain term that's kind of proportional to how much power or heat generation is there in the fuel pellet. And then the fuel loses energy because the fuel heats up and then you have cold coolant passing over it and you have heat transfer from the fuel to the coolant. That's a convective heat transfer. So this is my convective heat transfer term. It's like a constant times the delta T between my fuel and my mod. So this and basically what we're saying is that we're modeling the reactivity change as some delta due to like an external reactivity insertion plus how my reactivity ultimately changes because of the temperature and power feedback. Question?
What is that?
K is basically just a proportionality constant. And same thing with this funny zeta. Basically, this is just a constant that says the gain of my fuel temperature is due to like heat generation. So that yeah, if you this would kind of look like if you remember like if you're thinking about your heat transfer class, this would kind of look like a heat diffusion equation. This would look like your heat generation term, and then this would look like a loss of energy due to convection, where this quantity is like if you think about your convective heat transfer rate as like a convection coefficient times an area times a delta T. That is like baking in the convection coefficient in the area, and then that's the resulting delta T. So that's basically just an energy balance equation is fundamentally what that one is. And so this is helping you see why you take heat transfer, because ultimately heat transfer is going to end up coming into play when we start thinking about these systems and how they're when we get into that'll be basically like once you'll finish junior year, you kind of learned all of the fundamentals and then it's just applying everything. And that's like what senior design is. It's like you've got your neutronics from like these classes, you've got all the mechanical engineering stuff from like your mechanical courses, and then it's like let's design a reactor. Let's see how the neutronics and the power and the heat production kind of interact and interface with each other. So this is an example of how you would do that to make a point kinetics model that incorporated temperature feedback. So for intermediate time problems, that is when we can still ignore the fuel being depleted, but we have to consider the concentrations of fission products that come out. Those fission products are really important because some of them, like xenon 135 and samarium 149, they have very high absorption cross sections, which makes them kind of a nuisance in our reactors. We have to carefully monitor, especially xenon and samarium, because they can make our reactor very dangerous. Part of the Chernobyl accident was a not understanding the details of the fact that these fission products get formed as the reactor operates. And so you can put your reactor in a very dangerous spot because you can build up so much negative reactivity from these. Part of what happened is that they had so much xenon and samarium being built up that they had so much negative reactivity that they were trying to get the reactor turned on, and they were like, let's just remove every single control rod because like there's so much negative reactivity they can't get the power up, so they're just pulling control rods out and pulling control rods out. And you get to a point where you've removed all of the control rods and then you basically have no absorption and you very quickly go from a subcritical state to a supercritical state, and that was effectively part of what went wrong in the Chernobyl accident. So understanding about how these things vary with time is really important. We got to kind of account for these things to make a reactor be critical over its whole life. And we do a lot of different things to account for these products building up in our reactors. But if you can ignore them, then your point kinetics model is going to be fine, and you might just account for their effect by just accounting for making some time dependence of the K effective that incorporates how K effective goes down as these fission products get built up. And then if we talk about longer term problems, that's more of like what we're going to focus on today. And that is basically going to tell us, it's going to give us detailed knowledge about how the fuel changes as the reactor goes. And to know what happens with the fuel, you have to know what happens with the flux. So you really need to know like a detailed information about the flux history in the reactor. Um, and that's part of the complication. And the way that we get around that is we make a simplifying assumption. And the way to like kind of simply handle these depletion problems is to say, instead of treating the flux as a continuously changing function, we say that it changes slowly over time, such that over some little time step, the flux is basically has a constant shape. So we're saying that the flux can be approximated as this flux shape that only varies with position and energy, but doesn't vary with time. So in some little time window, we're saying the flux is constant. If we treat the flux as constant during that time window, then we can do calculations of our system with that flux being a constant. And we can consider the reactor going from one state to another with constant flux values along the way. And this approach, we call it the adiabatic approximation. Adiabatic approximation. And in this adiabatic approximation, we're basically treating the flux shape as being constant as we go through a series of changes. So it's like you go through a series of changes where the flux is constant during each of those individual time steps. And then basically within each interval, you're just kind of doing like a steady state calculation based on the constant flux. So when we are analyzing the composition of a core, it's the main things that are going to affect that core composition is the fact that fission products build up and also our fuel gets depleted. And that's the whole focus of chapter 8 is understanding and quantifying those changes. So we were kind of already talking about how the fission rate and the capture rate densities, they both depend on what quantity did both the fission rate and the capture rate depend on? If we go back to like our equations that we were writing before, what was it that both the fission rate and the capture rate both depended on? They both depend on the flux, right? And so if both of them depend on the scalar flux, P of R and E and T, well, if they both depend on the energy dependent scalar flux, we know that the energy dependent scalar flux depends on other things too. Like it depends on what materials are in my reactor, right? Like if my reactor is all control rod, then my flux is probably zero because any neutron that's in there is just going to get absorbed. So the flux, the reaction rates depend on the flux, but the flux depends on the core composition. It depends on the core composition. And it depends on that through the N of R and T, through the numbered densities of the components in my reactor. So this is a coupling because the changing of my composition changes my flux, which changes my composition, which changes my flux. So that is what complicates doing depletion analysis. And the way that we get around that is with the adiabatic approximation, where we say, we know that both of these are changing at the same time, but let's just assume that the flux is constant. Let's calculate how much things would be built up, how much isotopes in my reactor would be built up or depleted based on that flux being constant. Let's recalculate based on at the end of that time step what that new composition looks like, and then let's recalculate the flux for the next time step. And that's kind of like what the adiabat. Oh yeah, sure, yeah. Mhm. So, yeah, we get around that complicated coupling of the flux and the densities by just assuming that that composition changes slowly enough that we can assume the flux is constant over each time step where we do these calculations. And then we can use this adiabatic approximation to figure out what that phi looks like at each individual time step. So that'll give us an understanding of both like the flux history in our reactor and the composition history in our reactor too. So we're going to define some terms for the model. T with a subscript 0, that's going to be our initial time, which we're going to set to 0. And in these calculations, we're assuming that the reactor is in like a full power critical state at time 0. We're going to use a delta T to represent the depletion time step. That's the time interval over which we assume that the flux is constant. And that initial flux shape, we're going to use that phi sub 0 of R and E as the symbol for our initial flux shape. And this flux shape is what we're assuming is constant over each individual time step. So those are like kind of the starting terms, and then we can talk about the approach for this and kind of how we can go through a series of these static calculations. So basically what we're saying is that at start, we're in full power and we have some known like nuclide composition in our reactor. And then we also know at the beginning, we know that the flux has some initial shape. Maybe the reactor's initially critical, so we can like do like a diffusion calculation to say this is what the flux shape would be at the beginning. And then we're gonna assume that that flux shape is constant over this first time step. And so basically what we're saying is that in the first time step, so from 0, when t is between 0 and t1, where t1 is just the initial time step time, which was 0, plus the time step, over this first time step, from 0 to t1, we're saying that the flux is approximated as a constant phi 0. So we have this, we're saying that it's constant. And then we're using the fact that it's constant. We're going to use this to compute the corresponding amount of corresponding nuclide composition at the end of the time step. So this would give us N of R at the end of the time step, so at time t1. So it's like we knew what the initial composition was. We knew what the initial flux shape was, and we used all of that information to compute what the concentration of my isotopes would be at the end of that time step. And then knowing what the concentration is at the end of that time step, we recalculate a new flux shape, and then we use that flux shape as a constant for the next time step. So we're going to get a new flux shape phi1 that's going to come based on the changes in our composition from composition at time 0 to the new composition that we had at the end of time t1. And using that composition at the end of time t1, we recompute the value of our flux, which would be constant over the next time step. So this is going to give us our phi of R and E and T, which we're going to continue to approximate as just a constant flux shape, but over the next time step. So this would give us the phi1, which would be the new constant flux shape over the next time interval to go from t1 to t2. So that phi1 would be constant over that next time step. And then you would just repeat this procedure. At the end of time step t2, I would get a new numbered density, n2, and then I would use that numbered density at the end of that time step at t equals t2 to get a new flux shape, phi2, based on that number density. And then it's just an iterative process where you use the old phi to compute the new number density, you use the new number density to compute a new phi, which remains constant for the next time step. So You can basically do that to predict the amount or the concentrations of any nuclide in a reactor as a function of time. And the way that we're going to set up those equations is using the same kinds of approach that we've done to find the time evolution of like a population. And what was the like the mathematical approach that we did for that? If we wanted to find like the how a population evolves with time? Or if we wanted to just say like how does some it doesn't even have to evolve with time if we're just looking at like some like a reactor and we're asking like what are the gains and what are the losses and um yeah, and the idea there is that we're just doing conservation. That's all that we're doing when we say change rate equals gain rate minus loss rate, we're basically just writing a conservation statement. And those conservation statements mathematically, absolutely, they say that the rate of change in our population, which could be the neutrons in our reactor, it could be the nuclides in our reactor. The rate of change of that population is just equal to all the ways that that population is gaining. So it's equal to the rates of gain of that population minus the rates of loss of that population. So when we're doing these production and destruction equations, we're setting them up based on a conservation statement. And the conservation statement includes all of the gains and losses that could result from our nuclides, all the different ways that our nuclides could be produced in our reactor or lost in our reactor. So we had already talked about some of these losses, and we had already talked about how decay, fission, and capture are all both gains and losses, depending on what nuclides we're talking about. So I wanted to kind of think about what some of those losses might be a little bit more. So like if we have a loss due to radioactive decay, um, an example of that would be like a fission product would decay. So we could produce a fission product, and then that fission product decays. That would be an example of a nuclide fission product decays. That'd be an example of a nuclide in our reactor being lost because of a decay reaction. Um, so nuclides can be lost from decay. Nuclides could be lost from capture. Like we were talking about how 238U could absorb a neutron. And I guess I'll say captures a neutron. And then that would mean that the 238 is being lost from our population because it became something else. And then losses due to fission to like 235U could fission. And then 235U would be gone, at least in an isotope, one of my 235U atoms would be gone, and it would produce some new fission products. So that would be like the gains due to fission would be that we produce fission products. So production of fission products. Sorry, one sec. My tablet died, so I'm gonna pull up my notes on my phone. Okay, and then so we have two other gains examples to talk about. A gain due to decay could be just any decaying fission product is gonna decay and then becomes something else. So basically, fission products, yeah. So fission product decay is what we could say here. And then that is going to builds new fission products. Or we can just say builds up new nuclides. And then the last would be gains due to neutron capture. We were talking about how like 238U could capture a neutron, then go through a transmutation process, where then 238U becomes plutonium 239. So you could basically have transmutation. So like 238U becomes 239P. And that would be an example of a transmutation due to neutron capture. So when we look at these production destruction equations, this is all that they're saying. It says that the rate of change of my population is due to all of the rates of gains minus all the rates of losses. And we're going to have terms in our equations that account for all of these possible losses and all of these possible gains. I think this is probably, I think this is like the most important understanding to have, because if without this understanding, if we look at the equations, we might get scared and we might think like there's so much going on here, but this is all that it is saying. Um, so so yeah, we're basically gonna, just like we had done before, once we know how to set up our conservation statement, and once we know what all of the gains and losses are, we could start formulating like an actual mathematical equation here using the functional form for my gain rates and the functional form for my loss rates. So that's kind of where we're going from here. Um, each of these equations is going to be differential equations because the rate of change in the density of the nuclide in our reactor, that's going to be like a dn dt. So that's going to be the differential part. And then the right-hand side is going to look like all of my gains minus all of my losses. Um, when we talk about the gain terms, we're going to have gains and losses that account for all of the different nuclides that are being produced and lost. So for the loss terms, usually if a nuclide is lost to fission, it could also be lost to capture. Whereas the nuclides that are born out of fission are different than the nuclides that are born out of capture. So if we think about the gains due to fission and capture, they're not going to be like mathematically related, whereas the losses due to fission and capture are going to be mathematically related. They're basically going to have the same functional form because it's the same nuclides that can participate in a reaction that makes them fission or a reaction that makes them capture. And if we think about the grouping here, we're going to have the fissions and the captures both as a loss term. And those are going to be kind of like, we could think of those as a combined loss, where if I think about the reaction that I get, if I add up all of my fissions and all of my captures, what is that going to give me like in terms of my different cross sections? If I did like capture plus fission, what reaction would that tell me about? Absorption, right? It would basically be the total absorption. And so for the losses, we can kind of group those two together and just have a total absorption term. So that would represent the total absorption rate density. So that's all we're saying here, that we know what all of these gains and losses are, but technically the fission and the capture can be replaced with an absorption term because the fission plus the capture is my absorption for the losses. If that's okay, then we can start introducing the terms that we need to start telling apart the different populations that we want to keep track of. Because it's like we've basically got like fuel atoms, we've got fissionable atoms, we've got fission products. We want to be able to keep track of these things individually. And so we're going to introduce some indexes to our terms to be able to do that. Because ultimately, other things that we might want to account for is like in a reactor, you have multiple regions. In those regions, you have different nuclides, like you have your fuel and you have your cladding and you have your coolant. And the materials, the nuclides that are present in the fuel and in the cladding and the coolant are going to be different. Those reactions are going to have different, depend on different like energy ranges. So we could have different energy groups over which we're considering these reactions. And then we're talking about depletion and how the composition changes with time. So we also want to talk about these quantities at various time steps. So we're going to have some indexes. We're going to use H, a lowercase h for the region index. And so that's just a number that tells me like 1, 2, 3, or 4. Am I in the fuel or the clad or a control rod or just various regions of my reactor that I could have are denoted with a region index H. We're going to use a lowercase k for the nuclide index. So that's just, we have a k, k1, k2, k3, k all the way up to like 100 for all of the different nuclides in our reactor that we're keeping track of. Like one of them might be uranium-235 and another one might be uranium-238. And we just assign each nuclide a number and nuclide index, and that's what k is. We're gonna use the same group index, so little g for like the energy group index. So that's the same terminology that we used when we were doing like multi-group diffusion question.
It was uppercase.
It's a lowercase. Sorry if that looks like an uppercase. Kind of. Yeah. I don't think we have an upper, yeah. So it'll kind of look like this. And then we're gonna use an S for the time step index. And so that's just saying like at what time step are we in the problem? We had kind of like started when I was introducing the adiabatic model, and it was like from T0 to T1. That would be the first time step, T0 to T1. And then so that would be S equals 1. And then S equals 2 would be the next time step from like T1 to T2 and so on. So ultimately, we're going to track the atom density of every nuclide that's in our core. So we could use an N subscript K to just talk about the atom density of every type of nuclide that we have. And we could have our reactor be composed of different regions, in which case, if each region volume is V sub H, then the total volume of our core is just the sum of all of the individual region volumes. So the volume of the core is just a sum from H equals 1 to the number of regions of my VH. So hopefully that makes sense. Like if I had a clad and a coolant and a fuel, then the volume of my core would be the volume of the clad plus the volume of the coolant plus the volume of the fuel. If I had three regions, there would be 3 terms, and adding those up would give me the total volume of my system. And then we're saying within every volume, like for every region volume, we are approximating this NK, which could be a function of position and time. And we're going to say any position information, we can just lump that with whatever region I have, so that this is going to be approximately NK of T with some H region superscript. So in that way, I don't have to have my number densities vary as a function of position, and I can just say within my fuel, I'm tracking these compositions. Within another region, I'm tracking compositions, and I'm just tracking how those compositions evolve with time instead of how they also evolve with space. From there, we are going to apply the adiabatic approximation. So for every time step TS, we're using the adiabatic approximation. We're going to be approximating the flux as the value at the start of the time step. So this, in terms of our notation, this would be phi at S minus 1. And this varies with position, could vary with position and with energy. So that S-1 is just the fact that when we do the adiabatic model, we always start the flux being constant at the beginning of the time step. So that's what the -1 is telling us. Um, and so we have some atom density, Nk, in some region H, and we're saying that this flux shape is going to be constant during every time step within each region. And we're also going to assume that the cross sections are like region specific. So I don't need to make the cross section be a function of position. I can just say I have a cross section for each individual region. So for example, for my cross sections, instead of having it be a function of position and energy, I can say I've got a cross section for the region H that varies with energy. And a similar thing with the scalar flux, that I don't have to use the scalar flux as a function of position. I can just say I have a certain flux within each region. So my flux at some time step would look like phi of s in the region H as a function of just the energy E. So basically all we're saying is that within each region, the materials are constant, or at least the what I have in one region is different from another. So I'm going to have like very different materials in region fuel compared to region coolant. Therefore, within those regions, I can just basically say whatever the cross sections I have are just based on what materials are there in that region. And similar thing with the flux. Um, and then these things could also vary with energy, but ultimately what we're probably going to end up doing is just looking at different energy groups, considering these quantities in different energy groups. So like taking these expressions, integrating them over some energy range, and then using like group averaged values. That's the last thing that we could do. So then our flux would have a subscript S to tell me my time step. It would have a superscript H to tell me about my region, and it would have a superscript G to tell me about what energy group do we have. And similar thing with our cross sections. Our micro cross sections would have a region index and a group energy index. So these are kind of like the details behind the terms and how we're taking them from like an energy dependent representation to effectively a constant representation where we're looking at things within specific energy groups, within specific regions, and at individual time steps. So with that, the only other thing that we have to do is introduce some nuclide indexes so that we can start differentiating what kinds of nuclides do I have in my reactor. So we're doing the adiabatic approximation. These production destruction equations are going to look like this. And we're thinking about what the gain terms look like, what the loss terms look like. We have different kinds of gains and losses depending on what materials I'm talking about. So we introduce some indexes to tell apart the different kinds of nuclides that we have. We use I as the fissionable nuclide index. So I equals 1 might be like uranium-235, or I equals 2 might be like plutonium-239. And just depending on how many fissionable nuclides you would have various I indexes. The transmutable nuclide index, we use Z for that. So those are nuclides that can produce the nuclide K after they capture a neutron. So 238 uranium would be like an example of one of these transmutable nuclides because it can capture a neutron and then it can produce a new nuclide that we're just calling K. Um, and then any decaying nuclide, we're going to use the symbol J for the decaying nuclide index. So ultimately, we're saying if I have a nuclide I or Z or J, these nuclides could have a reaction, like my I nuclides could fission, and those could produce new isotopes. The Z nuclides are transmutable, so they could absorb a neutron and then produce the nuclide K. And decaying nuclides could themselves decay. Type J nuclides could decay and then produce the nuclide K when the J nuclide decays. So with those indexes and with the equations that we've developed, or at least with the kind of conservation statement that we've developed, if we were to fill in the mathematical form for all of those equations, we would get something that looks like this. So this is the production destruction equations in their full mathematical detail, where the left-hand side is the rate of change of some nuclide K at some time step S in the region H. And the rate of change of this nuclide is due to all of the ways that that nuclide could be gained minus the ways that that nuclide could be lost. And notice how we said that the nuclides could be born because of fission. So the first term is a fission term. And this fission term represents type I nuclides. Remember, I's are fissionable nuclides. So these are fissionable nuclides that fission. And in the fission process, some fraction of those type I nuclides become the nuclide K. That's what this Y from I to K is the fission yield, and we're going to define this in a second, but that fission yield is just a multiplier on our fission density term, which says what fraction of my type I nuclides become the nuclide K that I'm trying to keep track of. So this is basically the production of type K nuclides from the fission of a type I nuclide. This term, notice that I have like a sigma capture and a number density and a flux. So this is like my capture rate density. And so notice that this summation is over all of my I nuclides. All of my nuclides that could fission, there would be a fission term for each of those nuclides. Any nuclide that can capture has the Z index. And what we're keeping track of here with this gamma factor is the fraction of captures in Z nuclides that produce the nuclide K that I'm keeping track of. So this is basically fissions of type I that produce the nuclide K. This is captures of nuclide Z that produce the nuclide K. And this is decay of J-type fissionable nuclides. And then we have another factor, alpha, that talks about the fraction of decaying J nuclides that produce the K nuclide that I'm tracking. Yeah.
So they just like probably
They're just fractions. They're even more simple than that. It's just a ratio. And I'm going to define those in a sec. But I just wanted to like talk through these terms real quick just so that we can hopefully see it just is like kind of a complicated way to the equations mostly look complicated just because of all the superscripts and subscripts, but try not to get lost in that and hopefully this kind of makes sense. And these last two terms, this is the decay of the type K nucleon. It's decaying and it's producing every time that type nuclide decays, its amount decreases. So I have a loss of my K nuclide because of decay. And I also have a loss of my K nuclide because of absorption. Anytime the nuclide K absorbs a neutron, it could become something else. So I have a loss due to the decay of K nuclides, and I have a loss due to the absorption of my K nuclides. And K are just the ones that we're tracking. So K is like the index that we're tracking, and then we have all these other groups, the I group, the Z group, and the J group that contribute to the K group through these various interactions. So these are all of those terms, the individual terms in my equations defined. And yeah, so notice those last three terms are defined here. They are the group yield. Y is the group yield. So that's like the fraction of type I fissions that produce the nuclide K. This gamma factor, it's the probability, or basically it's the fraction of captures of type Z nuclides that produce the type K nuclide. And then alpha is like a decay fraction. So it's the fraction of type J nuclides that decay and produce the type K nuclide. Question? S is the time step index. So you would basically, you would solve this equation for every region. So like this would be simplified if I had a one region reactor, because then the H subscript would go away. S would be the time step. So it's like this would be like an iterative process. where like in a computer science sense, it's like you solve the equation at one time step, and then you update your solution, and then you solve it at a new time step. So this equation is basically an equation that you would apply at every single time step, and you would use it to recompute what your atom densities are based on the constant flux. So like this, we would apply the adiabatic approximation to this, and that's something that I'm gonna kind of talk more about as we go forward. Now that we've introduced the equation, we'll talk about how to simplify it, how to better understand it, and then ultimately how to solve it. So yeah, don't be intimidated by the equation, right? It's just that conservation equation. It tells us change rate equals my gain rates minus my loss rates. Um, that first term goes over I, which goes over all of my fissionable nuclides. The second one goes to all of my transmutable nuclides that could capture a neutron and produce the K nuclides. And then the last sum is all of my decaying nuclides of type J that could produce the type K nuclide. And each of those sums are set up so that they're telling us what fraction of each of these groups contribute to the group that I'm tracking. Um, Recall that when we talked about fission, like in the first week of class, we talked about how when a nuclide splits, it doesn't just always have the same two fragments, and the same two fragments aren't equal in equal mass. This distribution is showing that usually one of the so this is a probability density function. So it's what's my probability to get out of my fission nuclides of a various mass number. When we get two, so the most common thing is that we get one nuclide out of fission that has a mass number around like 95, and then we get another nuclide out of fission that has a mass number like around 140. And so, and so these are the nuclides that are most probable to come out of fission, but I can get any nuclides on this curve. So technically when I'm fissioning, like one of the things that I just think is so cool about fission reactors is that as they operate, they basically produce like every element in the periodic table. So in your spent fuel, once you turn that reactor on, you're producing in small fractions, like every, gold and platinum and anything that you could see on the periodic table, basically most isotopes that are on like the isotopic chart, they'll be produced in our reactor. And so we introduced this gamma factor, the fission yield, as a quantity that basically just gives us a fraction of it's the probability or the fraction that the fission of a type I nuclide produces a type K nuclide. So it's just the fraction or the probability of type I nuclides that fission and then produce the type K nuclide. These values for those yields are found experimentally. So we can look at tables of data where people have already done these calculations. And the only thing that we end up really needing to do is normalize all of these yields. And the way that we normalize them is such that if we were to add up all of the yields of all of the different nuclides that are so if uranium-235 is I, and uranium-235 can fission, and it can produce a K nuclide, which is like it can produce every single mass number possible, then what we're saying with the yields is that if we were to add up all of those little fractions, they should add up to the sum that represents the total number of fission products that came out of the reaction. And almost always when a nuclide fissions, it splits in two fragments. So we basically always will normalize these yields to 2. It's normalized to 2 because every fission reaction produces 2 nuclides, and the yield is just saying what fraction of the of fissions produce a nuclide of type K. And so K is going to go from 1 to the number of nuclides produced from fission which could basically be like every nuclide on the periodic table. So K could go possibly up to like 250 or 300. K could be in the hundreds, which means that if you want to do a very detailed like isotopic depletion calculation, you've got to keep track of like hundreds of different nuclides because your fuel fissions and produces basically everything on the periodic table. So we could take those general equations and we could start to simplify them a little bit. Um, what we can probably do is just take those the cross sections and the fluxes for each group, and we could apply a one group approximation. So we could like integrate over the whole energy range. And if we were to do that, then that would drop the G subscripts, sorry, the G superscripts. Basically, if we make a one group approximation, we integrate over the whole energy range, then there's only one energy group now, and so the G superscript goes away. We could also start simple and assume that we just have a one region reactor. Like maybe our reactor is just a sphere of fuel. So if we only have one region, then we could drop the H superscripts. And then our production destruction equations would look like that. So we already kind of have made things a little bit nicer on the eyes by just getting rid of any energy dependence by integrating over all energies and then saying it's only one region. So we don't have an H superscript index and we can just assume that these calculations are just for the one region of my reactor. Um, Ultimately, these equations are a coupled set of equations, and it's a coupling of all of the different nuclide densities because this is an equation for the type K nuclide. So if K goes from 1 to 250, then you would have an equation for every single nuclide. You would have an equation for K equals 1, K equals 2, K equals 3, K equals 4, all the way down to K equals 250 or however many nuclides we need to keep track of. Yeah.
For instance, H.
Oh, sorry. It's H. My handwriting just made it look like an M. Yeah. Yeah. So all these H and HGs, they go away. Um, And so, yeah, you're going to have like 200, however many nuclides you have, you're going to have a bunch of these equations. And when you write the right-hand side of this equation, you're going to have a varying ends. You're like on the right-hand side of the equation, you might have N1 and N2 and N3 and N4 and N5. So the equation for like N1 is going to depend on lots of other ends. And the equation for N2 is going to depend on lots of other ends. So these equations are coupled because in every equation, the solutions for like nk are a part of each equation. Um, so basically what we'd be trying to do is solve for all of the atom densities. And everything here is, all of the coefficients are constant. So these equations can actually be like they lend themselves well to being solved like in a computer doing like linear algebra kind of calculations. Um, so in a practical approach, you wouldn't actually yourself keep track of hundreds of nuclides. If you ever had to do something like that, you would use software that can do it for you. So there's a software called LIMS that is the way that you could do your depletion calculations. And it basically has a library of all of the different values, all of the different nuclides that could be produced, all of the different kind of ratios and how one nuclide can produce another. So when we're doing like detailed fuel analysis, these are the kind of tools that people would be using so that they don't have to like analytically solve those big coupled depletion equations. Um, so if we start talking about solutions to these equations, um, um, yeah, so when we solve these equations, we use the adiabatic approximation. At least that's the easy way to do it, so that those fluxes, that phi of S1 at the previous time step is known. The cross sections are all found and they're pre-averaged. And so during the time step, you can then solve those equations for each atom density. And then the value of that maximum time step is going to vary depending on lots of different factors, like how fast is my core composition changing? If my core is changing very rapidly, then I probably need a smaller time step to be able to account for those changes. Whereas if my changes are slow, then I could probably get away with a larger time step. Um, the other thing is, how do those changes affect the flux distribution? Because we're assuming the flux is constant, but if we make the time, so if we make the time step too large, we're assuming a constant time step, we're assuming a constant flux over a time step that's too long, which would lead to inaccuracies in our solution, as well as just the accuracy of the numerical scheme that you use. Like, if you're solving these equations numerically, you're going to have to do something to approximate the derivative here. Like, you might approximate the derivative as like a finite difference, or maybe you do like a second order scheme or a third order scheme. Depending on the order of your method, you would have different varying accuracies of your method. Um, and so, yeah, those are going to be the things that might affect my time steps. In general, the way that you would solve these equations is by going through these steps. So at the start, we know what's happening in our system. So that's at the time t of s minus 1. At that initial time, we know the initial composition and we know the initial flux shape. So the way that we would do it is that at that initial time, we would basically find all of our multi-group constants, like all of those sigma A's and the sigma F's over the group. We would find those by like energy averaging all of our cross sections based on how much material is there. Um, and then once we had all of those cross sections, we could solve the multi-group diffusion equation to get the flux as well as our K effective. So like once we know the materials in our reactor and we know them for and we know all of our corresponding cross sections, then we could do like a zero-dimensional model calculation or some other calculation to say what's the flux in my reactor, what's the corresponding value of K effective in my reactor. And then once we knew the flux, and once we knew all of my materials, like all of my sigma A's, and we know the initial composition, we could solve those production destruction equations and get the NK, the density of all of my isotopes at the end of that first time step. And then once I had the densities at the end of that first time step, I could recalculate what the corresponding new flux shape would be. And then I could use that flux shape. I could basically, knowing what my new composition is, I could recalculate all of my group constants. I could recalculate my flux and my K effective, and then I could hold that flux constant over the next time step to get my NKs at the end of the next time step. So it's like it's this iterative process where the solution at the end of one time step feeds into the initial values for the next time step. So that's like a common numerical approach. You could use these equations to solve all of those NKs, and that would be the general iterative process that you would go through. Um, in terms of some other ways to simplify it, there's a thing that we can take advantage of called pseudo fission products. And basically the idea here is that we get a lot of fission products that don't really affect the reactor operation that much. So like if we build a fission product, but that fission product has no effect on our reactivity, then we don't really need to necessarily monitor those isotopes in a burnup calculation. So if it's something that has like a very low absorption cross section, we might not need to track it. If it decays into something that also has a negligible absorption cross section, we could probably ignore it. So what we basically do is we get a group of pseudo fission products and we get an effective yield that just basically is like a average of only the fission products that we care about. Um, so basically, to get this effective yield, which is the same symbol as the yield before, we just put a tilde on top, so it's kind of like an average quantity. Um, and the way it's defined is that the yield, the pseudo fission product yield, it's just the sum of my yields for all of the other fission products. So it's a sum of my yi to k for the group G. So that's all the pseudo fission product yield is. We say, what are the fission products that I actually need to keep track of? My pseudo yield is just the sum of the yields of all of those guys. And then the corresponding absorption cross-section of these fission products, the pseudo absorption cross-section, is a weighted average. So it basically looks like a sum over all of my K nuclides of my yi to K for group G times the sigma A for my nuclide K in region H in group G. And then that is all divided by, I'm going to do divided by like this, a sum also over all Ks of just my yields. So just my yi to K for group G. So this is the way that instead of having to keep track of every single fission product, we only basically we lump all of the fission products into one group. And then that group has a pseudo yield, which is the y with a tilde, and it also has a pseudo absorption cross section, which is the sigma with the tilde. And the whole point of doing this is that it simplifies our equations, it reduces the number of terms that we have, and these are defined mathematically so that the pseudo fission products basically give you about the same absorbing characteristics that you would have if you took into consideration all of the real fission products that you have. So from there, we can move into analytical solutions. We can basically simplify those equations quite a bit by making some assumptions like generally the way we'll start is by limiting how many nuclides we track. So like we could basically start with 9. Um, we might assume that there's only one fissile nuclide in our reactor. So like K equals 0 would correspond to that nuclide. We're going to consider 7 nuclides that are in the fertile to fissile conversion chain. So like my fuel nuclide could absorb neutrons and transmute into other things. So we're basically keeping track of the nuclides that are in that conversion process from the fuel absorbing a neutron to eventually becoming a new fissile atom. And so we'll track 7 nuclides in that chain. And then we'll assume that anything that fissions goes into this group that we call the pseudo fission products, which is the group K equals 8. And then we can do it with one group, so G equals 1, and we can do it with one region, so H equals 1. So in that simplified model, the material number or the nuclide index K is limited. And so this is what that would look like for a fuel that is based on a uranium plutonium cycle, and also for a fuel that's based on a thorium uranium cycle. So K equals 0 is the fissile material that you initially have. In both cases, we're assuming that that fissile material is initially uranium-235. And then in our fuel, we start with some fertile nuclide. So like in our uranium plutonium cycle, the fissile nuclide is 235. The fertile nuclide is U238. And as U238 absorbs neutrons, it goes through this decay process where like it absorbs a neutron and becomes something else. And these things go through decays, which end up producing these these nuclides in the fertile to fissile conversion chain. And each of these guys ends up being fissile, meaning, some of these guys end up being fissile, like plutonium 239 and 241 are fissile. Other ones are fissionable, like plutonium 240 and plutonium 242. So everything that gets produced here can either be fissioned or it's fissionable. So each of these things itself could absorb a neutron, could fission, and could end up producing these pseudo fission products. So in like a simplified production destruction model, these would be the nuclides that we might keep track of to understand what's happening with our fuel. And as well as what's happening with the buildup of fission products. And you could set up a similar simplified cycle with a uranium thorium cycle, where here you start with uranium 235 and you start with fertile thorium 232, and that becomes the thing that absorbs neutrons and produces some of these other isotopes in your fertile to fissile chain. Um, so this is the simplified form, right? If you wanted to do this in detail, you would probably have like hundreds of different nuclides that you would keep track of. This is how we can kind of do it in a simple, more manageable way. And so what we want to do is just kind of think about the initial loading of our fuel and how isotopes would be born as our reactor operates. So what we were saying is that the reactor initially contains uranium-235, and it also contains uranium-238. So K equals 0 would be like our index for uranium-235, and K equals 1 would be our index for 238. Uranium can do a couple different things. Uranium can fission, and if uranium fissions, it could produce fission products. Uranium could also beta decay and be lost from a beta decay. And then when we think about the things that are in my fertile to fissile conversion chain, I have uranium-238. Uranium-238 could also fission and produce fission products, but uranium-238 could also capture a neutron. So that's and 235 could also capture a neutron too. So there's kind of two possibilities. You either fission or you capture a neutron. If you fission, you produce fission products. If you capture a neutron, you produce a new nuclide. So when uranium-238 absorbs a neutron, the thing that happened, do y'all know like physically how 238 absorbs a neutron and then becomes plutonium-239, which would be like our K equals 2? Yeah, so that uranium absorbs a neutron and it becomes like basically uranium-239, but then that neutron, one of the neutrons in that nucleus will itself decay. And a neutron, when it decays, can become a proton and a electron. And the electron gets kicked out of the nucleus, the proton stays. And so that neutron basically converts into a proton, which means that the element changes. It goes from uh, uranium to plutonium because you added a proton. And then and so yeah, and basically so in that process of absorbing a neutron, beta decay, that's how you end up breeding new isotopes because the number of protons changes. And so you could go along this chain. Plutonium-239 could fission, or it could capture a neutron and produce plutonium-240, which would be like our K equals 3 nuclide. Plutonium-240 could fission, or it could capture a neutron and become 241, which be our K equals 4 nuclide. 241 could become 242, that would be our K equals 5 nuclide. 242 could absorb a neutron and become americium-243. That'd be our K equals 6 nuclide. And then plutonium-241 can actually itself is very compared to these other guys, like technically uranium-235, uranium-238, plutonium-239, plutonium-240, those are all radioactive. Those all could decay, but the half-lives for those isotopes is on the order of like hundreds of thousands to millions of years. So they decay so slowly that we don't really need to track them. Whereas plutonium-241, this half-life, it's like on the order, I don't want to say exactly, but it's like 10 to 100 years. But comparing to like hundreds of thousands or millions of years, that's like the one that is most, to the extent that any of them matter. Plutonium-241 is like the one that matters the most in terms of its decay rate, and it can decay into americium-241, which would be our K equals 7 nuclide. And then we're saying anytime something decay and anytime something fissions, it adds to our group of our pseudo fission products. So notice that any of these things that resulted in a fission all produced this fission product group. Same thing when our americium absorbs a neutron. It could fission and produce fission products. And all of those fission products are grouped together. And that's our K equals 8 group. So that's why it's nice to use the pseudo fission products is that we don't have to keep track of Like there might be hundreds of different fission products that are born. We don't have to keep track of 100 of them. We just lump them all into this group that we call the pseudo fission products. So this diagram is really important because it's kind of telling us for each isotope what our production and what our losses are. So anytime you see an arrow going to that thing, it is indicating that that thing is being produced by that interaction. And if you see an arrow going away from it, it means that there's a loss from that interaction. So there's only arrows going away from uranium-235, which means that in the conservation equation for 235, it should only have loss mechanisms. It shouldn't have any gain mechanisms. It should have a loss due to fission, and it should have a loss due to capture. Uranium-238, it should only have, it could have a gain due to production into 235 capturing neutrons and becoming 238, but then 238 would also have two losses from itself fissioning and itself being experiencing a capture. So this diagram illustrates what the production and the losses are for each nuclide. And if you were to start writing out what the production destruction equations are for every nuclide, it would look something like this. Notice that, for example, okay, so I take back what I said before. We're not assuming, so K equals 1 is the uranium-238. And we're not assuming that the production, this arrow shouldn't really go into the chain. So that's, just make sure we kind of note that this arrow does not go to here. So this is saying that uranium-235 is only losing because of fission and because of capture. So the fission plus the capture is absorption. So that's why the equation for uranium for isotope 0 looks like a flux times the density of that material times the absorption cross-section for that material. And then for K equals 1, which would be my uranium-238, notice that it also just has losses. It has a loss due to fission and a loss due to capture, which gives me overall a loss due to absorption. Each of these other terms in this equation is just looking at all of the gains and all of the losses and then expressing them in a mathematical form. Ultimately, each of these equations can be written in this matrix form, and then the matrix form is pretty easily solved. So that was kind of where I wanted to stop. When we come back, we're going to talk more in depth about these equations, solving them and applying them. So I think today we got a good understanding of how like to set up the equations and what the equations are telling us. And then next time we'll start more with solving them and applying them to better understand how certain isotopes build up and get depleted. So thank y'all for your time. If y'all have any questions, let me know. Otherwise,
Start again next.
sorry.
Let's just start again next.
Yeah. Yeah, if y'all have any questions, let me know. Otherwise, thank y'all for your time. Have a great rest of your day, and I'll see y'all on Thursday.
Did you ever think the readings book about it?
Yes, I just don't remember. It's probably in the notes.